Okay, in the previous lecture, we have been discussing about element approach of flexibility matrix method, and we have already seen the examples of a continuous beam, two-span continuous beam, and a plane truss structure analyzed through the element approach. Now here, an illustration of the same approach for a portal frame. An unsymmetrical portal frame is given. We have analyzed the same structure through structure approach already in one of the previous lectures. Now we are going to revisit and construct the same matrices delta and delta L vector using the element approach. That is it. Now essentially this is the structure to be analyzed. We have a column of length 10 meters and moment of inertia 4i here, a column of length 5 meters and moment of inertia I, second moment of area I is here, that is CD, a beam of length 10 meters and second moment of area 4i, that is BC over here, and the only load acting on this is an 11.2 ton load acting say along the horizontal at point B. That is it. The supports are fixed support at A and D. The first step will be to find out the degree of static indeterminacy, and that is equal to 3 as obvious from the previous sessions. Now structure coordinates are assumed in the structure by removing say joint D, by removing support D from joint, and assuming coordinates horizontal is the first coordinate, vertical is the second coordinate, and this rotation or rather the moment over here would be the third coordinate. These are the structure coordinates as is assumed in the previous section also. Now here I have divided the structure into 3 elements. This is the first element having coordinates 1 star and 2 star. The beam is the second element having coordinates 3 star and 4 star, and this column is the third element having coordinates 5 star and 6 star. They are the coordinates of the respective elements. Now we need to develop first of all the force transformation matrix. We know that the size of F in this case would be 6 by 3. It is number of element coordinates by number of structure coordinates. The first column of this would be developed by setting R1 is equal to 1. So when you put R1 is equal to 1, that is this force is equal to 1, and R2, R3 are equal to 0, R1, R2, R3 are nothing but the forces corresponding to structure coordinates 1, 2 and 3. So now if I put R1 is equal to 1 as it is given over there, and if you draw the free body diagram of the 3 parts of the structure, we are going to get for force equilibrium you require a force over here which is equal to 1, and for moment equilibrium this span is 5 meters. The moment produced by these two forces will be 1 into 5 anti-clockwise, so you require a moment of clockwise. For equilibrium this is 5. Further, we transfer these forces with their opposite signs to this joint in the beam. So this will be 1, this moment anti-clockwise will be 5. Again in the beam for equilibrium we will transfer this force or this moment with an opposite sign here at the other end. So this is 5 kNm, this force will be 1. So equilibrium of that beam is also satisfied. Further, when you come to this column, at this joint the force here will be 1 rightwards for equilibrium of the joint, force equilibrium of the joint, and this moment will be transferred to this joint, this member as an anti-clockwise moment equal to 5. So joint equilibrium is also satisfied. Now further, for equilibrium of this column we have to apply a force 1 over here for force equilibrium and a moment equal to 5 to oppose or to equilibrate this moment, and now the moment produced by these two forces would be 1 into 10, that is clockwise. So to equilibrate that, we require an anticlockwise moment equal to 10. So that moment at this joint would be anticlockwise 5. Now we can fill up the first column of the F matrix, which will contain essentially the forces corresponding to element coordinates when we set R1, the force corresponding to the first structure coordinate equal to 1, and the forces corresponding to the second and third, the rest of the structure coordinates are 0. So the force corresponding to 1 star would be anticlockwise 5, that is minus 5. Force corresponding to 2 star would be anticlockwise 5, so minus 5 itself. 3 star, it is plus 5. 4 star, minus 5. 5 star, it is plus 5. 6 star, it would be 0. So these are the elements of the first column of the force transformation matrix. That is fine. To develop the second column, we set R corresponding to the second structure coordinate equal to 1, and the forces corresponding to the first and third structure coordinates are zeros. Now, if you go ahead to draw the free body diagram of the pieces as in the previous case, this is R2 is equal to 1. Let us set this force is equal to 1. So equilibrium of this member will necessitate a force here equal to 1 opposite to this one for equilibrium. That is fine. This joint net force is equal to 0, so the force over here would be upward and equal to 1. Further, for equilibrium of the beam, there should be a downward force at the other end equal to 1. Now these two forces create a moment of 1 into 10, that is 10 anti-clockwise, and to equilibrate that we require a moment of 10 clockwise. That is about the equilibrium of that beam. Now when you transfer these forces to the same joint in the second member, for equilibrium of the joint we require a 1 upwards and a 10 anti-clockwise moment. That is fine. Now equilibrium of this member is to be considered. We should have 1 downwards and 10 clockwise. So that is R2 is equal to 1. Now if you collect all those terms to the second column of this, we have corresponding to 1 star, there is a clockwise 10. 2 star, we have anti-clockwise 10, so minus 10. 3 star, we have clockwise 10. Corresponding to 4 star, 5 star and 6 star, there are no moments. So 0, 0 and 0. That is second column. Now to develop third column, we put R3 is equal to 1, R1, R2 are zeros. If you go ahead to plot the free body diagram, in this case, we applied R3 is equal to 1. Equilibrium of this member necessitates anti-clockwise moment 1 here. Equilibrium of this member necessitates a clockwise moment 1 here for joint equilibrium and anti-clockwise moment 1 at this end. Further, joint equilibrium here will necessitate a clockwise moment 1 and anti-clockwise moment 1. That is the free body diagram of the members. Now when we transfer that to the column over here, we have corresponding to 1 star, minus 1, 2 star, plus 1, minus 1, this is plus 1, This will be -1 and this will be +1. So that is the force transformation matrix. Now we can develop the element flexibility matrix as delta star. Delta star will be given by the element flexibility matrix for element 1, element 2, element 3 arranged in a diagonal fashion. So we will get one by 60i outside, this number would be 5. We see that L is equal to 10 meters over there and I is equal to 4i. So when you substitute those numbers in the typical flexibility matrix for an element, a beam element, we are going to get the first term should be L by 3ei. So this is 5 divided by 6ei. We have I equal to 4i and L equal to 10 meters. So 5 divided by 6ei is going to be the first term. Second term would be minus 2.5 divided by 6ei. This is minus 2.5. This is 5. Now for the second element, the beam element, these numbers are going to be 5 minus 2.5 minus 2.5 and 5. For the third element, minus 5 and 10. It is pretty easy. Once you know the values of I and L for a span, we can develop it very quickly. The first term should be L by 3ei, second term is minus L by 6ei, this term is minus L by 6ei and this term is L by 3ei. That's all. We can develop that. All the other terms would be 0. We can flip zeros over here. Like that. That is it. Now we require the P star vector. P star contains equivalent joint nodes. Equivalent joint nodes for this span, this span, this span and this span. You see here corresponding to 1 star, 2 star, 3 star, 4 star, 5 star and 6 star. If you find out the equivalent joint nodes, we are going to get 0 because corresponding to 2 star, 3 star up to 6 star, we are going to get 0. But the moment produced by this 11.2 ton will be available only here. If you draw the free body diagram of this structure, when this support is released or removed, the force over here (11.2 tons) will be transferred only to this support, and the moment here would be, this is going to produce a clockwise moment of 11.2 into 10. So for equilibrium we require a moment anti-clockwise equal to 112, which is 11.2 into 10. Where is it? That is a free body diagram. Of the released structure. Now we can pick up the values of P star from that very easily. The P star will contain 112 anti-clockwise, so minus 112 is the first element, then there is nothing, so 0 corresponding to 2 star, 3 star, 4 star, 5 star and 6 star. That is it. So everything is in place. We can now construct this delta matrix by transposing F multiplying with delta star and further F develop delta L vector as F transpose delta star P star. If you do that, we are going to get delta as equal to 1 by 6 Ci 750 375 minus 150 375 2000 minus 225 minus 150 minus 225 and 60. That is the structure flexibility matrix, which can be observed as symmetric. Delta L vector (1 by 6 Ci) common factor 1400 minus 8400 and 840. If we compare with the matrices delta and delta L, which are derived, or rather which are constructed using the structure approach earlier, you can see that these two are one and the same. Delta matrix here and delta matrix there in that approach are one and the same. Delta L vector here and the other approach are one and the same. The only advantage of this case is that we have a systematic approach in developing the flexibility matrix and the delta L vector. And for completeness, the solution is given by solving the equation delta L plus delta matrix into R vector is equal to delta. Well, delta is the displacement corresponding to structure coordinates. Applied displacements correspond to structure coordinates, and they are zeros. They in fact account for the support settlements and support rotations. They are zeros over here. So if you solve this, you are going to get R as equal to minus 7.68, 3.29 and minus 20.86. We may draw the bending moment diagram also by substituting these numbers to corresponding to these coordinates. If you do that quickly, let me do it over here. The final free body diagram. This force is 7.68. Minus sign is accommodated as leftward sign, leftward arrow mark. This is 3.29. The moment is anti-clockwise, 20.86. So equilibrium at the other end would necessitate a force of 7.68, a vertical force downward 3.29, and an anti-clockwise moment of 17.64. So if you apply the condition sigma m is equal to 0, to equilibrate this moment you require a clockwise 20.86, and for equilibrium of 7.68 into 5 you require another moment. The sum of those two would be 17.64 over here. Now further, if you proceed further for the equilibrium of this beam, This force is 7.68. There is a vertical force of 3.29. Clockwise moment of 17.64. Here, at the other joint, equilibrium, downward force of 3.29. Rightward force of 7.68 and a clockwise moment of 15.36. This moment will be 15.36. This force is 3.29. Leftward force here is 7.68. And there is an applied force to the right of 11.2. So that is going to add to this with a minus sign, and the result of the 7.68 to the left, 11.2 to the right would be a rightward force of 3.5. This force is 3.52. This force is 3.29. And the moment here would be 19.84. So bending moments at the joints are available, and we can draw the bending moment diagram. This is 20.86. $17.64. This also is 17.64. When you connect them together, here you have 15.36. This is 15.36, and here 19.84. Straight line. That is the bending moment. Fine. So, an illustration of the element approach of flexibility matrix method is given through a portal frame. That is the essence of this section.